said, Jade Thompson from SKF. I have worked for SKF for just over 2 years now, but my background is oil analysis and reliability for the last 14 years. And I now champion a division for SKF called RecondOil in the UK, and I provide global support for that as well. But today we're going to talk about lubricant condition monitoring as a condition monitoring technology. People usually say, oh yeah, we do oil analysis. We do condition monitoring and we do oil analysis. So we're going to try and show today that it is a condition monitoring technology and some ways of using it in that way. So I've already explained who I am, but why I'm here today. So we're going to hopefully share some knowledge of lubricant condition monitoring. That will be oil analysis and grease analysis. We're going to go through a couple of case studies, and we're going to show how to utilize data as reliability and performance indicators. Hopefully by the time you leave, I can change your perspective on oil analysis and grease analysis and merging it as a really important part of your predictive technologies maintenance strategy. So what is lubricant condition monitoring? Today you've already seen, well, you will see some of the ultrasonics. You've seen some of the vibration from James Sylvester. There's some inline sensors that people can use as well for lubricant condition monitoring. But what we're going to focus on today is the lab monitoring. So this is where we are taking samples of oil or grease and sending it away to a laboratory for some in-depth analysis. All the other three technologies are absolutely a form of lubricant condition monitoring, but a direct form is when we get to the lab. Does anybody in this room, just put your hands up, use any form of lubricant condition monitoring with the labs today? Good stuff. So there's a lot of people in this room that take oil samples, grease samples, and send them away to labs. That's really good. I'm going to ask you guys that question again at the end. So we'll start with what a lubricant is, really, really basic. We're not going to go too technical today. So a lubricant is not an empty body of fluid or grease. It's quite a complex structure of hydrocarbons, which is the chain you can see on the top right. That's about as technical as we're going to get, but it's quite important to understand, because any lubricant failure mode that you encounter in one of your assets is usually going to cause or is a result of them hydrocarbon chains breaking down. Them hydrocarbon chains are what separate metal components and keep our bearings running smooth, friction-free. So we're going to talk a lot about them hydrocarbon chains today and how analysis indicates something going wrong with them. So the main function of a lubricant is to reduce friction. We want to reduce as much friction in a system as we possibly can, and that's things that ultrasonics and vibration detect. We also want to reduce foaming and emulsions in systems because, as we've just said, they break down them hydrocarbon chains, and then they're the only things keeping your assets running friction-free, well, as friction-free as possible. They're also there to improve load balancing. James spoke about slow speed earlier. Load balance from a lubricant in slow speed applications is super important. If you're not using the correct lubricant in a slow speed application, you're going to have serious issues. Sealing, cooling and transmission, they're also improvement functions of a lubricant. And then the last few are where we put additives into a lubricant to achieve this. We have wear and corrosion protection, oxidative stability, and also cleaning functions. They're usually in compressor and engine oil lubricants. So that is a really basic what is a lubricant, and it's the same for oil and grease. Grease is an oil with something transporting it and keeping it in place, but they are made of the same chemistry, the same formulations. So just to expand on that a little bit so it makes sense as we go through, a grease is a finished oil which is carried by a soap, which we can call a thickener, a soap. Some people will call it a sponge. and it's designed to make sure that the oil is where it needs to be lubricating. So for example, in a bearing housing, if it's oil filled, but it frequently starts and stops, the top of the bearing will run dry for the first element of startup. So we'd use a grease to make sure that the oil is where we left it last time we turned the machine off. So now we want to look at when do we use lubricant condition monitoring and when should we use lubricant condition monitoring. And this is oil or grease analysis. But for the rest of this presentation, I'm probably going to say oil analysis because that's what I'm used to saying. But when I say that, I mean grease as well. So hopefully everyone recognises this curve. It's a P2F curve. I think we've all spoke about it on the podcast with Chris. So hopefully everyone knows what it is. And we should use the P2F curve a little bit through our maintenance strategies, especially to decide on when should we use oil analysis and how often should we use it. So if we think about what the P2F curve tells us, it lets us know which technology is going to notify us the earliest of a specific failure mode. So for example, we've got a gearbox and we want to know if there's any corrosion happening in there. Which technology is going to let us know that the fastest? So with oil condition monitoring, we can kind of foresee something like that happening way before it does. Ultrasonics and vibration are fantastic. I'm not going to say anything other because Chris and James are sat right in front of me. But with oil analysis, we get maybe 200 ppm of water in there. We can foresee that that is what's going to start happening 12 months down the line. And we can foresee that somehow water is getting in there. So we're quite far up the P2F curve if we're using it correctly. And that's what we'll look at through this presentation today, is how to use it correctly so that we can use it at the earliest stage of a failure mode possible. The red line on this P2F curve is cost. So if we cross over that red line and we don't use things like oil analysis, vibration analysis and ultrasonics, it gets much more expensive. So the later we see a failure mode occurring, it's going to cost much more money. Usually, once we cross over, it's already past the point of us putting something in place to either limit that on or resolve the issue. For example, if we stick with water in a gearbox, if we identify that early, plan in a seal change, remove the water from the oil, we've prevented possibly bearing changes, overhauls of the gearbox, or a failure. So laboratory analysis is looking at three things, whether it's grease or oil analysis. And the first category that we look at is contamination. We want to look at, is there anything contaminating the asset? Is there anything contaminating the lubricant? Is it chemical or is it physical? And by finding contaminants, even in really, really small doses, we can foresee a lot of issues that might happen, but we can also choose the right path to solve that. So we then look at wear, because that's the next thing that will start occurring. So we've looked at contamination. We do up to 30 tests on each sample usually, but we've looked at contaminants. We've done all the tests we need to establish, is this lubricant contaminated, what with, and is the asset causing that contamination, or is it ingressing from the external environment? And then we look at wear, so all the tests that give us an idea of any wear occurring. And again, we don't just want to see there's 50 ppm of iron in there, it was 40 last time. We need to look at why is that wear occurring, merge it with the contamination results, and we need to look at ratios to other wear elements, but we'll go through these with case studies in detail a bit later on. Then we've got the chemistry category, and this is looking at what should the lubricant look like, what does it look like now, what's the deviation of change, and again, as always, what's possibly caused that, what can we do to resolve it. It might be we need a completely different type of lubricant in there because the hydrocarbons are being mechanically sheared, it's not the right lubricant for the job. Or it could just simply be that we haven't changed the oil for 10 years and it's the first sample we've taken, it's just been neglected. So we're looking at contamination, wear and chemistry. And again, it's not just the oil we're looking at. The whole idea of oil and grease condition monitoring is asset reliability. It's not about usually the oil condition itself. The oil is a component within the system, and it's the system that we're trying to look after. So with oil and grease analysis, there's 4 different ways we can use this. And in our industries that we work in, we should probably at some time use all of these. So there's specification, where we're making sure a lubricant meets specification and it is as it said. I was speaking to someone in here today, someone who I've known quite a long time and worked with before, and they did some analysis on a lubricant that was delivered to site. It wasn't actually the lubricant it was meant to be. So it is important to do them double checks and make sure that we're carrying out the tests that will confirm to us, is this delivery as it should be? Is it contaminant free? Is it ready to go and put into my critical asset? Because essentially, if we install a lubricant into an asset which is contaminated, it's like installing a faulty bearing. Nobody's going to dream of doing that. No one would pick up a rusty bearing off the side and install it. Then we've got routine oil analysis or grease analysis, which we will look at a specific case for. And this is where we are sampling on a routine base. We could almost marry it to preventative maintenance. We're routinely on a time-based manner collecting samples so that we understand condition. Then we've got failure analysis. A failure's occurred. Hopefully we've been carrying out routine analysis, but if we've not, we can still maybe do some root cause analysis with some more in-depth tests than what we usually do on routine, but we will also include the routine test. The failure analysis is super important because it can give us specific wear modes. James was showing us earlier how he compares the vibration to the part at the end. We've got a similar story with that as well, but using oil analysis today. Then suitability analysis. We looked at the hydrocarbons. If we're repeatedly getting an issue with viscosity of a lubricant, which is essentially its grade, or I'll probably get shot for saying this, but its thinness or thickness, it's its resistance to flow, how viscous it is. If we're constantly getting issues with that, it might be that we're shearing the hydrocarbons. So we do some suitability testing to understand, are we using the right grade of oil and do we need to change it? I work for an OEM. OEMs put a lot of work into telling us what lubricants we should use in our assets, but it's theoretical. They cannot cater for every single application, process, and a lot of us will use assets in scenarios and processes where they're not usually used. So we do have to optimize that slightly, do some routine analysis, and then do some suitability testing and decide, actually, we should be using a 320 grade here rather than a 220 because we're running it at 80 degrees instead of 60. Hopefully this all makes sense so far. So we've got an example here of routine oil condition monitoring. This was a user that does really, really frequent analysis. It's a public sector customer, so it was a safety reason they were doing this analysis. And we monitor all the wear, contamination and chemistry parameters for these lubricants. And all of a sudden one day we see a massive increase, as you can see on the top graph, in phosphorus, shortly followed by copper. And this is in the rail industry, but this was one train that we can see on the top graph. Luckily, we're getting weekly analysis. So we very quickly decided, let's speak to the rail customer. And we said, Mr. Customer, you're using a different additive pack. That's because we've got really high phosphorus. And that's affecting copper in the system. Speak to the engineering team, they speak to procurement, and the EP oils that they were looking at buying were 20 pence a litre cheaper than the normal oil that they use, so we just decided to get the one with a P in it. Obviously, people don't understand in procurement and sometimes in engineering the massive difference there is between an EP gear oil and a general gear oil. So what happened is one of the bearings on one side of each cab of this train had been corroded by the phosphorus additive almost immediately, to the point where all the trains that had oils changes done, which are shown on the bottom, you can see how erratic the copper is on the right, because some of the bearings were fine, whereas others weren't. There was 16 trains altogether that had to come back in, and on each train there was 14 wheel sets that needed to be pulled out. You can imagine the downtime with that, and it was a long time ago now. At the time, you probably all missed trains because of this issue. But it's much more serious than that if these guys weren't doing routine oil analysis, because that bearing would have failed. And if we weren't doing this analysis weekly, that bearing would have failed quite quickly. If we look at the levels, I know I've not got the values on there for you, but you can see how quickly it correlates. So hopefully this shows you guys the value of using routine oil condition monitoring for something critical. If it's a non-critical small pump, we're not going to do weekly analysis. But if it is something critical that you need to know a week in advance if it's going to fail, then we should be doing weekly analysis. Then we've got the failure analysis. So on the left is an image of some wear debris analysis, and we mix this with routine analysis on the right. Routine test, should I say. But this wasn't an asset that was having routine oil analysis done. So it's quite difficult for us to say what's changed, but this was a catastrophic failure. So we'd not caught this before the failure because the customer had come to us after we'd had the catastrophic failure. So what this is showing us on the left is we've got every single wear mode possible in place here and occurring. So we've got a lot of adhesive and abrasive wear. So we couldn't really go back with a root cause to the customer. But what it did show is, one, they should be doing routine oil analysis, but it did show them the types of wear that had occurred up to that failure. We just couldn't root cause it down to one. If they'd have also been doing vibration at the same time or ultrasonics, they'd have definitely been able to root cause. But if we just look at the table on the right, it shows us the different categories of analysis. So on the right, we can see that iron is the main contributor there. So we should be looking at our assets and seeing what have we got in there, which is iron, chromium, copper. We can see it's quite a serious bearing and gear failure. Hopefully the people in the room that are used to analysis can see that. But using this type of post-failure analysis won't give us a massive amount of trends and information, but it will give us something to learn from, because we can then use these ratios of wear that we see to compare it to other gearboxes that are the same on site. This again was the public sector. It was something where public are using these assets quite frequently. It wasn't rail, this one, luckily. But what this allowed us to do was then apply this knowledge as alarm sets to the rest of the assets, so that we could see the ratios before a catastrophic failure occurred. Hopefully that makes sense to everyone. What we did have to do, because we've done this analysis and we can't really go back to a main root cause, is we had to get dirty. Like James said earlier, we had to get our gloves on, get on site, strip it down, and start looking at what had actually occurred. And the root cause, which we could only tell once we got on site and stripped the gearbox down, was an oil type mix, as you can see on the first left image. So they'd mixed a mineral oil with a polyglycol lubricant. It had caused a plug. On the middle image, that's a shaft with splines, and them splines had essentially been sheared because the oil galleries were blocked, so they were no longer being lubricated. So sometimes we do need to go and strip something down, have a good look, and do some more in-depth analysis, but visually and physically. So using analysis as reliability and performance indicators, if we look, I'm trying not to go too techie on this one, but if we look at the report on the right, it goes from right to left, the trends. So we can see what's standard and what is routine for this asset. So going from, if we look at FW and iron, we're going from 200 ppm, and it's fairly consistent, and that would be what we would class as normal running wear for that asset. It's not had oil changes in between there, it's just had oil top up. And then on the far left column, we can see quite quickly that something's changed quite drastically, and we can use that information to then start predicting what's caused it. If we look down at the bottom, calcium is also the same. It's not an additive in this example, it's a contaminant. But we also need to try and look at the rest of the contamination analysis on here. Usually we would see something creeping quite quickly, and we would be able to identify to the customer, you're going to have a wear mode start quite soon, which we could with this specific report. Also looking down at the bottom at viscosity, that is one main thing to keep an eye on, because the minute them hydrocarbon chains start shearing, that's when that viscosity starts to change. And that's when you do start getting serious catastrophic failures. On the left, we've got, hopefully everyone's got maybe a generator or an engine on site. On the left, we've got a trend of what we call TBN and TAN or TAN. And this is additive versus acid. This is an environment where quite frequently the oil has to be changed, and it's just a way of trending that crossover and how soon it needs to be changed. Again, it is just a routine form of oil analysis, but it's very important we're doing it quite frequently. So the way we look at these as reliability indicators, on the right-hand side, we can see that the reliability is consistent until we get to the very first column where the failure starts. That's when we start looking at it as performance indicators, and we have to merge that with other technologies such as vibration or operational parameters to give a full story to the customer on what exactly is happening with that asset. With the type of data we use and the customers we work with, it's quite difficult for us to give specific assets and names because we're usually under an NDA because of the amount of information we can get from a report. So another way of looking at performance indicators is just tracking certain results for a specific asset. So we will always do a full set of tests, but for you guys, it's important to pick out the results of interest to you. If you've got a pump or a gearbox or even a grease bearing at the side of a steam line, it's very good practice for you guys to track things such as water and ISO code really, really closely. And sometimes pulling the data out like this and looking at your sampling rate, a little bit similar to what James was looking at earlier, how you're sampling and how often you're sampling, super, super important to be working out how soon is that failure coming and when can we start going from a reliability indicator to a performance indicator. When do we know there's a problem actually occurring? We've stripped through that quite quickly. This is the second to last slide. So for us to be able to use all this analysis as a reliability or a performance indicator, we need to merge quite a lot of data, especially because we can't get on site and strip every asset that we've done some oil analysis on or grease analysis, as informative as that would be. So what we do need for a decent lubrication condition monitoring program is sampling information. We need to know where it's being sampled from, what equipment is being used to sample it, and as much information as possible. If it's raining when you've took a sample, we need to know. Then we need to know specific component types. So writing gearbox 1 or gearbox A on some sampling information is not good enough. Ideally, we need to know, is it a helical gearbox? Is it worm and wheel? What size is the gearbox? How much oil's in there? And all that information allows us to determine correct alarm sets, but also for you guys in your equipment manufacturer's manuals, you should ideally have some alarm sets that they set, because they will know specific ratios of wear metals that you will see. We need to know the oil type that should be in there. If we look back at the one we've just looked at for a failure, that was a conflict between two oils. It was a massive incompatibility issue. If we know which oil should be in there, we can diagnose something like that happening really quickly. Someone could just be topping up 5 litres a week with the wrong oil, and it might take a while to become catastrophic. If the lab know that as soon as possible, we can catch it much earlier. And then oil changes when they are carried out. If we skip back to this slide, on the right, I know there's only been oil top-ups there. If there's been an oil change or a seal change, it massively changes them trends, and it ends up looking like a completely different lubricant and a completely different set of results. So it's really important to feed back to the lab when any maintenance activities have been carried out. And also history, if you forget to let the lab know exactly when something happens or when something changes, and also what's planned in the future. I've just been supporting a power customer with some cranes that they use and that are super, super critical on site. These cranes stop, it means a lot of work for site. And their service contractor has said that they need to overhaul these gearboxes. There's 16 of them all together, and they want to do a full overhaul based on the analysis. We only got the analysis in this week, otherwise I would have put this in to discuss and go through the case study. And it was based on lead, and the lead had trended down for the last 4 years and was still trending down, but the service company was really quite nervous just about the lead being in there. So what we've been able to do by using the maintenance history mixed with the machine history and the oil analysis trends is defer that overhaul by also, we've done some vibration there, we've used some other technologies, made sure we've looked at the data and merged it together to give the customer the deferral that they need to outage, because stopping them cranes now stops the rest of the plant, and it's quite a serious issue. So we've been able to use the data as a reliability as well as performance indicator to say to site and to say to the service provider, we're okay to continue using these and we're not in a serious risk, because this lead has trended down over the last 5 years. It's just we've not had an oil change or an oil top-up in that time until last year. Hopefully that makes sense to everyone. So looking at them case studies and what we've gone through, hopefully it all made sense, but how all the analysis works together and what we can use it to diagnose and give us a really good early indication on what's happening. Does anyone here really use oil condition monitoring? Does anybody look into it in that specific detail? Or do people think hopefully they maybe will go away and look at it a little bit more closely? Have I changed anyone's mind today?